Okay, so better late than never, right? So what I've done for this PowerPoint is put the solution in here. So if you're going back, you can always look at the textbook, but typically the textbook is kind of on the wordier side. So, but it's there if you need it. Now there's a part B. So this, let's look at this first before we move on to part B. We know if you just draw a quick vector diagram and you say, okay, a car is moving to the right. So that's a positive V. It's going from 0 to 26.8. What direction is your acceleration going to be in? First think, is it speeding up or slowing down? It's speeding up. Which direction is your acceleration going to be then? To the right. So your acceleration should mathematically come out to be positive. And it did. So we're on the right track. Now let's look at part B. Read up on part B while I erase part A. Maybe. Oh my goodness. This one. Part B is talking about a drag racer, I think. Yep. He deploys a parachute and slows down from 130 meters per second, super fast, to 45 meters per second in 3 seconds. So we want the acceleration there. So jot those down. Write down what you think is happening. You can draw a real quick, oh my goodness, this like this weird delay. There we go. Okay. So he's still moving this way. But this time, it's slowing down. Which way is the acceleration going to be? To the left. That's actually mathematically what should happen is you should get a negative A. And if you don't see that right away, don't stress about that because it will work out in the math. And even if you set up everything and a sign switches along the way, you're not, you won't get full credit, but you also will get a lot of partial credit as long as the physics is there. All right, so what's my VI this time? Write it in there. What's my initial velocity? What do you think, Mariana? So the drag racer is going from 130 to 0. No, it's not to 0, to 45. Yep, 130. And then what's my final velocity? 45. What other piece of information did they give us? Time. And they're asking for the acceleration. So you can write down your average acceleration is delta V over delta T. And I'm going to tell you that really it's okay to just write A. Because it's going to be the same acceleration the whole time. So you can actually just write A is VF minus VI. And remember that time, we're going to start the stopwatch when he lets go of the parachute. So we can just call it T. All right, so you should already start to see that this is going to be 43 minus 130 over 3. And that is obviously, hopefully, going to be a negative number. It got rid of my work. So 45 minus 130 all over 3. Who got it? Any virtual kids out there? You still with me? How about my virtual kids? Let's do a little test. Can you type Tuesday in the chat just so I know you're still with me? All my virtual kids, just type in a quick Tuesday or a T. T for short for Tuesday. what do we get? Negative. Oh, was that a virtual kid? 28.3 meters per second squared. It means that every second he's slowing his velocity down by 28.3 meters per second. So if he starts at 130, after the next second, he's going to be going at like 101.7. And then the next second, take away another 28.3 meters per second, and so on and so forth over those 3 seconds. Okay? All right, so the solution for that is there if you need it. Real quick check on concepts. We have a velocity time graph here, kids. Which car, A or B, has a greater acceleration and why? Who's got a greater acceleration?
Isn't it B because it's got a steeper slope?
You got it. So when you have a VT, remember the slope gives you acceleration. So the steeper the slope, the bigger the acceleration, the bigger the change in velocity over time. Okay, so that's the solution for that. Let's do another example. Go ahead, first step. What's our first step? Write down your 5 magic variables. VI, VF, delta S, A, N, T. This one's a little different. This doesn't give you VI and VF, but what does this indicate, this wording? And you're going to find that in physics, there's like typical problems and typical scenarios. And they might change up the objects that they're talking about. Like it might be a train, or it might be a car, or it might be an airplane, or it might be a cheetah, or whatever. But the generalized problems are roughly the same. This is talking about delta V together because it's saying it increases. So we don't necessarily care how fast it's going in the beginning or how fast it's going in the end. All we know is that it changed and it increased by 4.1 meters per second. So if we write it like this, what other pieces of information do we have? We want to find out time, and they give us meters per second squared. So do you have enough information? Well, let's look. We have our acceleration, and you'll see I just dropped the average because it's kind of redundant. I need to solve for delta t, or really, for t. Can we do it? We can do it. How do I get t all by itself? Here's my equation. A equals delta v over t. You want to pop numbers in? We can do that. 1.2 equals 4.1 over t. A little shortcut, just to dust off the algebra cobwebs. When you have something like this, if you just swap these two, it works. T is equal to 4.1 over 1.2. How long did it take that train to speed up? What's 4.1 divided by 1.2? .1 divided by 1.2. 3.4, do you agree? 3.4 seconds. Anybody disagree? And I make a lot of rightos, so always check my math. There's that solution if you need to go back and check it out. All right, moving right along. We've got a ferry. It makes a short run between two docks. It moves in the positive X direction, and it slows down to a stop for part A. What's the average acceleration? For this, I would just keep my positive X direction this way. So if he's moving that way, it's positive V. It's slowing down. What direction is my A going to be in? So if you're moving in the positive, and I'm slowing down, what's that? Yeah, to the left. Excellent. My virtual people are with me. All right. Negative A. So just keep that in mind. That's for part A. Go ahead. Pop in your 5 variables. Try it out. Do you guys want to be? Oh, no, they don't have computers out. Forget it. 5 magic variables, VI, VF, delta X, A, and T. So far, none of our problems have even looked at displacement, and that's okay. We're just getting our feet warm. So, it approaches with a speed of 7.4. Where does that go? It then slows to a stop in 12.3 seconds. So these are the key words. Slows to a stop should indicate what? Yeah, so your final velocity is 0. So pop a 0 in here, which means that my initial, when I start my stopwatch, it's going to be 7.4 meters per second. We want to know the acceleration if that happened in 12.3 seconds. So then you get your acceleration is VF minus VI all over T. So we get 0 minus 7.4 over 12.3. My acceleration, crunch that number. And think, has anybody been on a ferry before? Do they move quickly? No. No, they really don't move all that quickly. And they sure don't change their speed very quickly. That's why it takes 12 seconds to come to a stop. But what'd you get? Negative point. What'd you get, Paige? 0.6 meters per second squared. So every second he's only decreasing his speed by less than a meter per second. And look at that negative. That's beautiful. That's exactly what we anticipated. Now, for part B, it says the ferry returns to this other dock with a speed of 7.3. But be careful, because if he's moving back this way, what direction is he going to be in? What's my velocity, positive or negative? So you have to take that into account. And these are the little tricks where you're easy to lose track of. So take your time and think it through. He's slowing down. So what direction does my acceleration have to be? Remember, if you are slowing down, your V and A have to be in opposite directions. So if my velocity is negative, that means my acceleration has to be this way. And that is totally counterintuitive to what you're used to thinking, because you always think acceleration, I'm always speeding up. If my acceleration is positive, that must mean I'm definitely speeding up, and that's not necessarily true. So now that we've thought that through, we get VI, VF, delta X, A, and T. We want to know the acceleration for this part. It comes to rest in 13.1 seconds. What goes where? What do you think, Matt? You got VI or VF for me?
Would it be the same as before?
Almost the same.
Oh. Yeah, so that's 7.3.
And then 0, because it comes to rest. Then we're going to write our equation again, and you'll see that it just gets to be routine after a while. VI minus VF. So we get 0. What did I forget? I forgot this. Negative. Remember, the velocity is negative. See how easy it is to forget? So we get 0. Here's that minus sign. But then you have to put in negative 7.3 divided by 13.1. So what's a negative of a negative? Positive. So 7.3 divided by 13.1. We're going to have an acceleration pointed in the positive direction, slowing this down, and we get a 0. Who crunched it? 0. Yeah, I'll just leave it there because I'm running out of room. So you got to keep track of your positive and negative directions. Just think of it always as just directions. Don't get too hung up on the traditional thought of what positive and negative means. In physics, it means directions. Alrighty. There's your solution if you need to run through it. Let's move on. We only have a couple more. Maybe 3, 2 more. Oh, maybe 3. Here's our example. So we've got this boat. It's kind of cruising around in the marina. Anyone who's ever been on a boat, you know, you have to keep a low speed. But then as soon as you exit that marina, you can hit the throttle and go faster. So that's what's happening here. So we're going to count the time as soon as he exits as our starting point. That's when he's going to start to speed up. It gives us an acceleration. We want to know what is the velocity after he hits the throttle for 5 seconds. Try it out. Start with your 5 magic variables. See if you can match stuff up. How are my virtual kids doing? Where are we? I'm afraid to exit. I'll give you a hint. We're still not using displacement yet. We got everything we need. Oh no, they give us this. Hold on. We want to know the velocity after it has accelerated for 5 seconds with an acceleration of 2.4 meters per second squared. What's my initial velocity? Don't get tripped up on the fact that they call it speed. All they're saying, that's how fast. And we're just going to assume whatever direction he is in is positive. Unless they, they expressly tell us stuff. So my initial velocity will be 1.5 meters per second. So go ahead and write in your equation, plug in those numbers, and if you rearrange this, you're going to see that it turns out to be this. This is one of those kinematic equations. So these two things really say the same exact thing. This is one of your kinematic equations. So we should be able to pop in some numbers here. We should get 1.5 plus 2.4 times 5. What would we get for VF? 2.4. You guys are very quiet. Did anyone get it? $13.5? What'd you get? Did I fill the numbers in right? 2.4 times 5 plus 1.5? Okay. Because that's always a possibility too. That's why we like to double check everyone. Like, you check me, I check you, you check one another's. So that means, so he's starting out at 1.5 meters per second. He throws the throttle in for 5 seconds. His boat is accelerating. It's speeding up 2.4 meters per second every second. So if he does that for 5 seconds, this is what his final velocity is going to be. Look what part B has you do. We're finally going to find displacement. You're going to need that equation sheet. So pull up that equation sheet. I'm going to erase this stuff, but we can write in what we found here. Let me use a different color. 13.5 meters per second. Now, can you find me an equation that's going to help me find displacement, delta x? You've got everything here. So there's more than one way that you could find this. There's more than one way to find it. Let's find a good equation. In fact, try it now. Write down the equation you're going to choose in order to find displacement or delta x. And remember, here's one thing. When you look at your equation sheet, kids, you're going to see ones that look like this. This is just a little hint up here. If you have this, if you have that, look at what delta x really is. Do me a favor, subtract xi from both sides. These guys go away, right? What's xf minus xi? What's final position minus initial position? It's displacement. So you could see these equations either way. Just get used to that. That when you see it's separated, it's okay. When you see it put together, it's okay. Did you find it? It is. It's your change in position. And how you calculate it, you take your final minus your initial. So yes, delta is change in. So this is your change in position. In other words, it's your displacement. So that's what we're looking for. We've got it all. So we can plug in our numbers and we can make sure we can use our calculators efficiently. That's sometimes half the problem. But remember, if you show me all this work, if you show me this, if you then plug your numbers in the right way and write it out, but then you botch the algebra, you still get most of your credit. So 1.5 times 5. I'm going to be lazy and drop my sig figs a little bit, and it's okay. And then 2.4 is my acceleration. Then my time is 5 squared. Don't forget about that. So he's going 7.5 meters. And then the acceleration part, whoops. Is another 30 meters. So my total displacement, my change from the starting position to where I end up, should be 37.5 meters away from where I started. Double check my math though. And your solution is here if you need to go back. Oh no. Oh, we have this example. This is a little bit more about just seeing, and we don't necessarily have to run through it, but they're saying, you know what, if you have a drag racer and he accelerates at 7.4 meters per second squared, so every second he increases his speed by 7.4 meters per second, how far will it travel in 1 second, 2 seconds, 3 seconds? So let's assume he starts at rest. So if we did our 5 variables, my initial would be 0. My final, my displacement, that's what we're looking for. And then our acceleration is a 7.4 meters per second squared. You could look at this and you could say, okay, well, after 1 second, how far did I go? And then we want to say, well, after 2 seconds, let's just set it up and let's eyeball it. If we want to know how far, we want to know our displacement. So we're going to come down, we're going to use this guy again. I can also write it as my displacement. I'm going to subtract x initial from both sides. And I'll get initial velocity times time plus 1/2 the acceleration times squared. What's my initial velocity in this problem? 0. We love when things are 0 because they drop out and make life a little bit easier. So now all we really have to look at is 1/2 of the acceleration times squared. This stuff you could do in your head or really quickly on your calculator. What's 1/2 of my acceleration? What's 7.4 divided by 2? All right, so we're going to say 3.7 t squared. How far does he go after 1 second? So we pop a 1 in here. We square it. What's 1 squared? 1 times 3.7. So he goes 3.7 meters. Cool. What if he's been traveling for 2 seconds, though? Now it's 3.7 times what? 4. So that's a lot further. And then if you take 3 seconds, 3 squared is 9. So he's going to go almost 37. It's 9 times 3.7. So you can see when you're accelerating, you're covering a lot bigger distance every second you're traveling that way. So that was the visual idea for this guy. So you could go through, you could do it. All right, here's one, another typical type of problem. Let me explain what it looks like. So you're traveling in this direction. That's going to be my positive V. You see a deer over here. This deer is 20 meters away. We want to know if you slam on your brakes and slow to a stop, here's my slow to a rest, is that deer going to get hit? So let's think about this. If we're moving in the positive positive direction for velocity and we're slowing down, we know my acceleration's got to be negative. So keep that in mind when you set up your 5 variables. My initial, my final, my displacement, my acceleration, and my time. Now let's go looking into the problem. It says a park ranger, blah, 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 sees a deer 20 meters ahead. The ranger is driving at 11.4 meters per second in the positive direction, immediately applies the brakes, and slows with an acceleration of magnitude 3.8. That's just tricky language to stress to you that that is the size of the acceleration. We know as genius physics students, how do we write that? Positive or negative? Negative. So that's a negative 3.8 meters per second squared, and then my velocity is a positive 11.4 meters per second. He slows to what? 0. It asks how much distance is required for the ranger's vehicle to come to rest. They give me that 20 meters. Does that go in there? That's just how far away the deer is. So that's saying from where you apply your brakes to where the deer is 20 meters. They throw that in there just kind of like to test that you really know what you're talking about. So we're actually trying to find this displacement. We don't know anything about how long it takes. So look at your equation sheet and tell me, do you have something there that doesn't have t in it? And if so, jot it down. I'll give you a hint. It's in the box. Look at maybe this guy. Will that work? Do we have enough info to solve for displacement of the car to find out if Bambi lives? How are my virtual kids doing? Okay? Unmute if you're confused. Be careful. This is negative. You're stretching. What's my VF? Oh, something goes away. Yay, we love that. Because it's 0. Remember, he's coming to a stop? So we're going to have 0 on this side. We're going to have 11.4 squared plus 2 times negative 3.8 delta x. We're solving for delta x. So if you want, you can crunch your numbers now. We'll round this. We'll say 0 is 130. 2. Now watch, I'm just going to say, well, let's just do it this way. Plus negative 7.6 delta x. So I have to bring over the 130. And then I divide both sides. So check my math. What does that even tell you? It tells you that if you apply your brakes, if you're moving at 11.4 meters per second, you apply your brakes, you are going to need 17 meters to come to a stop if that's your acceleration of your car. Does Bambi live? Yes. How do I know? Because Bambi's 20 meters away. You stop at 17 meters. So there's still 3 meters in between the two of you. All right, so that solution is up there for you too. And we're gonna, do we have time? Oh, we have 1 minute. Take a look at this, see if you can try it out, and we'll start here, I guess, on Thursday. On Thursday, I want to go over your quiz as well. I want to let you know that the reason I need that work uploaded to Schoology, you can go back in, you can view the quiz, you can write out your solutions, because a lot of kids can get partial credit. And I can't give credit just for answers because I don't know where they came from. So make sure if you have not uploaded that work by 2 today so that I can go through and try and grade them tomorrow and we can talk about it on Thursday. How are my virtual kids? On a scale of 1 to 5, 5 being, yes, I'm rock solid with this. Tell me where you stand. You too. How comfortable do you feel after a 4? 4? Get in there, try the homework. Okay. All right, my virtual kids, give me a 1, 2, 3, 4, 5, and have a great day. I'll see you on Friday. Although I lost them. I don't know where we are.
Have a good day.
You too, hon. Thank you.
Have a good day.
You too. Thank you. Where's screencast?